Welcome to York Universe, the astronomy and astrophysics podcast written and presented by the students, faculty, alumni, and friends of York University. You will now find us wherever podcasts are distributed. I am Mahin Himani, one of your hosts this evening, and I am joined by the Observatory Director, Dr. Elena Hyde. Tonight, we are broadcasting live from the Allan I. Carswell Observatory on the Keele campus in Toronto, Ontario, Canada. York Universe broadcasts live every Monday at 9 p.m. local Toronto time or currently 1 a.m. Tuesday Universal Time. We also run in concert with our online public viewing or OPV run by the observatory staff. And we have some good news. We have clear skies this evening, which means they will be sharing wonderful live and archival images and also answering your questions in the simultaneous YouTube chat. So feel free to post in any questions you have for our observatory crew. To follow our live show or learn more about us, please visit yourq.ca/science/observatory and follow the link to our online public viewing chat on YouTube. For any questions or comments about past shows or suggestions for future topics, please email us at observe@yourq.ca. You can also connect with us on Instagram at YourQ Observatory, PixelFed at Allan I. Carswell Observatory, or on Facebook at Allan I. Carswell Ops. All of our programs are free, but if you would like to donate, please see our website at yourq.ca/science/observatory. We will be monitoring the YouTube chat for questions and also posting fun content throughout the show. So let's dive right in. How are you tonight, Dr. Hyde? Do you have any observing suggestions for this time of the year for our listeners?
Yeah, always. Of course, there are so many things up all the time. It makes astronomy one of the most fun sciences because there's literally always something going on. We do actually have a really fun near conjunction right now with Mercury, Jupiter, Venus, and the moon, all kind of following the sun down as it sets, which should be pretty spectacular, but really hard to see if you don't have a clear view to the west. So if you want to get some good viewing in, I would say your first step would be look to the west, and if there's any tall buildings in your way, maybe go to a different location. We are looking at it's actually tomorrow is the closest approach for the Moon, Venus, Jupiter, Mercury meetup. So this is Monday, the 15th of June. And of course, we do have that fabulous meetup low in the horizon. So your best chance to see it is to wait until around 8:30, 8:45. Do not look directly at the sun. Wait until it's just below the horizon. But then just above, right where that sunset is, you should see some really nice bright planets in the sky. So those will be really, really cool basically this week. We do have Mercury going even more visible, which is good because it's always really hard to see so close to the sun. It's going to hit its greatest elongation on June 15th, which is today. So it'll be good for a while. And after the end of this month, we're kind of going to lose sight of Mercury for a while. So if you do happen to want to catch a picture of Mercury, now is the time. And of course, this being June, we're gearing up for the solstice. So in the northern hemisphere, we're about to have our summer solstice, just as the winter hemisphere has its winter solstice. That's going to be on June 21st. And there should be a nice full moon at the end of the month just to round off, you know, a very good June. So I believe June's full moon is called the strawberry moon. Something about strawberries being in season. Uh, but it should be a nice one. And overall, I'd say there's always lots and lots of fun stuff to look up and see. Is there anything you're looking forward to?
Um, Actually, I have a recommendation, which is something I'm looking forward to as well, is go for a walk near sunset time. So you get to see a sunset, and then right after sunset, you get to see all of these planets, and keep your Stellarium app handy on your phone so that you can, quickly point it up and see what planets you're looking at. Because sometimes if you're not very, if you don't know as much about which planet is which, it can be confusing. So having the app handy can be very useful. Um, but I always enjoy looking at the planets being close to each other, and you can always get like really pretty pictures that way too, which fit, on your screen easily. Um, so I'm really looking forward to that.
Yeah, absolutely. And of course, with phones now, I will say even a cell phone camera can do a reasonable job, especially
Mhm.
if you set it into night mode and let it do a longer exposure after the sun goes down. And there it really is not going to be any better chance to see Mercury. Mercury will be the dimmest of the three planets. Venus will be the brightest. So you kind of get three bright, interesting planets to look at. Um, and of course, the moon is always nice, but it's very, very thin crescent at the moment.
Which also helps with being able to see the planets easily. So I
Yeah.
guess,
Well, we're already fighting the sun. I wouldn't want to have to fight fight both the sun and the moon.
Yeah,
Oh,
so
geez.
since we have all of these recommendations for observations over the next months, now I would suggest that we dive into this week in space and astronomy history. And the first item is by Dr. Hyde, so I'll hand it over to you.
Yeah, of course. It's always fun to go back in history. And of course, we're talking about things we can see in the sky. But in astronomy, we're also interested in all wavelengths of light, including those we cannot see. And sometimes, in particular, those we cannot see. So the human eyes can only perceive a very small, limited range of light. It comes in many other forms, and one of those forms is X-rays. So X-rays are really really fun. We did not know about X-rays as humans up until around the late 1800s. So 18 1894, 93. Well, around 1895, the first detection of electromagnetic radiation happened. William Röntgen, a German physicist, and this is 1890, so we're going back in history a ways. He detected X-rays in a really, really interesting time because he's probably one of the luckier scientists I've read about because he managed to discover and detect X-rays, build devices for them, take the first X-rays humanity has ever taken, and win a Nobel Prize for it. The first Nobel Prize, mind you, in physics, all within just the space of, basically a few years. So he had a really good go. From about 1895 was the official um, time of the discovery, and the X-rays were named for X radiation, which was just because it was an unknown type of radiation. It's an unknown type of light. So light is radiation, and of course we kind of had known about that light could be split into different colors, shall we say, because throughout human history, people had been playing with crystals and prisms, but figuring out what it all meant and pinning down the different wavelengths is a long, probably much longer history than we can go into. But X-rays are very interesting. Their wavelength ranges from around 10 nanometers, which is 10 to the minus 9. So you have to put nine zeros before you get to put a one. So really, really, really small. They're so incredibly, incredibly small, all the way down to 10 to the minus 12. So this is a trillionth, 1 trillionth the size of a meter. So you'd have to divide a meter into a trillion pieces to get a picometer. So X-rays are extremely energetic. They carry a lot of energy with them in this extremely, what's called a sort of extremely short, um, uh, extremely short wavelength, high energy range. So the 10 nanometers to 10 picometers, tiny, tiny, tiny wavelengths, which means the wave going up and down happens in a tiny, tiny, tiny space. So this wave is going up and down a lot in any amount of distance that a human can think of, which means that it can go through things like your skin and muscles and most of your living tissue and until it gets to your bones, where some of it will start to bounce off. And this is how X-rays are made. So X-rays, because they can go through most sort of living tissues and construction materials, like wood, no problem to X-ray through that. But you can look for things like weak points in your metal frame or weak points in your bones that are inside your tissue that you can't see, and you can look at it without cutting it open, which is great for medicine and I guess engineering, but also really, really cool for science. So X-rays being discovered and people figuring out about them was a really, really big deal. I cannot overstate the amount of press and hype that this was getting at the time. The discovery from Wilhelm Röntgen was announced in 1896, and there was a German newspaper, Die Presse, which was German for the press. um, they publicly announced his discovery of X-rays in 1896 in January, and they right away they realized the potential for all kinds of things, medical diagnoses, and he then got the Nobel Prize from the very first Nobel Prize in 1901, roundabouts of this month. So he got that Nobel Prize right about now. So pretty fun. But back in 1901. So he only had to wait, that's, depending on how you count the years, 4 or 5 years between his discovery and actually getting the Nobel Prize. So many scientists have never gotten it. I would be one of those, but quite a few people only got them late in life. So the Nobel Prize, of course, being the set of physics prizes that were put in place by the will of Alfred Nobel, who died in 1896. And basically, in his will, he said, "I want to be known for, establishing these prizes." And I believe they started off with only five. And yeah, um, the very first recipient for the Nobel Prize in Physics was Wilhelm Röntgen for the X-ray. Now, it is worth noting that the Nobel Prize does have some caveats behind it. Um, it's notorious for leaving people out, and in particular, of course, we do have to make a special note that they are very, very bad about doing any kind of sort of equity in their prizes. Um, Only five women have ever won the prize in the history of the Nobel. Marie Curie, of course, still is incredibly famous. Maria Goldberg-Meyer, Donna Strickland, who won in 2018, Andrea Ghez in 2020, and Anne Louis, who ran in 2023. So, it's starting to do a little bit better. But it's noted that this is out of the hundreds of people, there's not very many of them, and a lot of them are shared. So you will see things like people getting half a prize or a third of a prize or a fourth of a prize. Um, Now, in astronomy, X-rays are also our good friends, but these X-rays come about from a really interesting, really interesting history. So when we were first coming up with what are um, what is electricity and how does it work? We had things called, cathode ray tubes, which were basically early types of electrodes which would convert current, basically the starts of the beginnings of lead acid batteries. But it took a really long time for humans to figure out what was actually going on. There was all kinds of um, different types of discoveries happening around the same time. The electromagnetic theory of light was just kind of getting popular. And, we had a lot of different disagreement about what light is. Is it a wave? Is it a particle? And now, today, we actually accept both explanations. So, early on, people didn't know what was going on, and actually early theories of light include that basically your eyes were thought to emit rays, and I'm talking early as in before the 1500s. So early in human, one of the first explanations of how vision might work would be your eyes would emit these vision rays, and your vision rays would go out and detect, what was out there for you. Um, Now we know that that doesn't happen. The light comes from a light source and has to bounce off of an object and come into our eyes. But it just goes to show how much disagreement there was. We didn't even know that there were electrons at this time. So, having a good picture of physics meant now we can kind of go, oh, well, of course, this makes lots of sense. Can have X-rays and gamma rays and microwaves, and we can have light of any size, we think. So, but at the time, it was very revolutionary, and the X-ray um, equipment that they had was, uh, I would say, shoestring would probably be the best way to put it, because you had a lot of things being done on the fly by people who didn't really know what X-rays were. Now, X-rays are really useful, but they're actually kind of toxic as well. So when people were initially playing with these X-rays, the technicians and the people using the X-rays didn't really get protection. And what they found is that, it is actually pretty dangerous to you in high doses. Um, so, now we know that. But in the early 1900s, 1908, it was all very new, very exciting. Lots of experimenters ended up with burns. Actually, even Nikola Tesla apparently got X-ray burns at a demonstration. So, you know, this was a little bit of a experimental time, but a really interesting time, and a lot of people playing with electric currents and vacuums and creating X-rays until the point, of course, when 1906, eventually Charles Barklow would discover that X-rays could be scattered by gases, and that elements could have a characteristic X-ray spectrum. So this means that you could see X-rays emanating from various elements. And of course, this will lead us to X-rays in astronomy. Lots of fun.
Yeah, that's very interesting. It did make me think of how like this reminds us how the discovery of electromagnetic spectrum basically is vital to modern existence. Like nothing from, our cell phones, Wi-Fi, a lot of the medical treatments, none of that would exist if we didn't know so many of these emissions and radiations. And then it also translates into how fundamental science does help society. And like the electromagnetic spectrum is one of the greatest examples of that. Because if people weren't interested in understanding some of these things just by pure curiosity, we wouldn't be here today.
Yeah, and if Röntgen and Tesla and all these other scientists had been out getting X-ray burns and who knows what else, we might not have found any X-ray stars.
Uh-huh. Which is a great segue for the next story. So I'm gonna jump right into that. Um, so I have a different starting today. So I want to talk a little bit about failures. So failures are not always bad. And it may sound like one of those things we tell ourselves to feel better when things do not go according to plan. But this turned out to be true in the discovery of the first X-ray star. On June 18th, 1962, a failed experiment led to the detection of Scorpius X1, the first known X-ray star, and ultimately launched the field of X-ray astronomy. So, as you may know, our beautiful home Earth atmosphere blocks X-rays, which means that X-rays from space cannot be observed directly from the ground. And despite this challenge, the existence of solar X-rays had been predicted in the mid-1940s, and researchers were beginning to develop ways to study them using balloons and sounding rockets. Sounding rockets carry instruments above much of Earth's atmosphere for a brief period of time to make certain scientific discoveries and calculations. So, one of the scientists who became interested in this area was Giacconi, working with physicist Bruno Rossi at American Science and Engineering, which is a private think tank founded by MIT professors. Giacconi became interested in other objects emitting X-rays the way the sun does. And at the time, most scientists doubted that such sources would be bright enough to detect. Nevertheless, Giacconi and his team developed highly sensitive detectors and designed a rocket experiment to search for X-rays above Earth's atmosphere. Interestingly, the experiment was not intended to discover an X-ray star. Instead, the team hoped to detect solar X-rays reflected off the moon. On June 18th, 1962, an Aerobee sounding rocket carrying the experiment was launched from White Sands Missile Range in New Mexico. The flight lasted only a few minutes, but the results would have a lasting impact on astronomy, as we will see. The experiments failed in, of course, the original objective, which was to look at the X-rays reflected off of the moon from the sun. Um, but the team found something that they weren't expecting. So the detectors recorded an intense source of X-rays coming from the direction of a constellation called Scorpius. And this source later became known as Scorpius X1. And the observations revealed an evidence of diffuse glow of X-rays spread across the sky, now known as the cosmic X-ray background. The discovery demonstrated that the universe looks very different when viewed in X-rays. Objects that appear relatively ordinary in visible light can become some of the brightest objects in the X-ray sky. Giacconi quickly recognized the significance of the result. Observing the universe in X-rays had the potential to reveal entirely new classes of astronomical objects and phenomena. What began as a failed attempt to study reflected solar radiation became the birth of X-ray astronomy as we know of it today. Over the following decades, X-ray observations ended up revealing things like neutron stars, black holes, supernova remnants, hot gas in galaxy clusters, and some of the most energetic phenomena in the universe. Scorpius X1 itself was also later identified as an X-ray binary system. So initially they thought it was just one star, but later they found out that it was a binary system, which also helped in understanding the mechanism behind the star. And what was going on was that the matter from a normal star was pulled onto a neutron star, heating to extreme temperatures and producing large amounts of X-ray radiation. So Giacomi then, after this discovery, continued to play a central role in the development of X-ray astronomy throughout his career, helping transform our understanding of high-energy universe. And in recognition of these contributions, he was awarded the Nobel Prize in Physics in the year 2002. And today, the field of X-ray astronomy traces its origin back to the rocket flight that lasted only a few minutes and an experiment that failed to find what it was originally looking for. So, in the case of Scorpius X1, one of the astronomy's most important discoveries happened because things did not go according to plan.
Very true. And of course, the people involved kept their eyes open, um, which is you never know. Keen observing definitely was a factor there. But don't give up might be another good one because it turns out that data was really, really useful.
Yeah, I think there are things in the history of science where people kind of miss very things that if we now look at them, they're very apparent and very obvious, but like people at the time missed it. So I think that in a lot of the discoveries, as you said, it's about like keeping your eyes open and looking at all of the facts very carefully.
Yeah, well, this is one of the great things about science is you can discover what you were not looking for. And that's, if you are truly open to the idea of discovery and looking for anything odd, you can find that thing that you didn't even know could be there. And that's really, really cool. And this is, of course, Scorpius X1 being a binary system has so much going on for it. It is a really, really, really fun, you know, area of study, I would say, just because whenever you have binary systems, like in this case, you have a star feeding, was it potentially a black hole, I think you said, and creating an X-rays a system. This tells us so much about how those stars might evolve and what kinds of things could go on out there in the universe. And because of the high energy X-rays that are emitted, you can find out things that you wouldn't be able to find out normally. Maybe it was a neutron star actually, but but really really cool stuff. And there was a great I don't know, paraphrasing. If you shoot for the moon and miss, at least you're still amongst the stars. So they shot and they missed, but they still got something.
Yes, I totally agree. I really enjoyed getting to know about this story and also relaying it to our audience today. So it looks like we have now hit the midway point of our show. So I'm going to go ahead and remind everyone that you are listening to the York Universe, the Space and Astronomy podcast from York University. We are broadcasting live from the Allan I. Carswell Observatory at York's Keele campus in Toronto, Ontario, Canada. Please look at our website at yorku.ca/science/observatory to join the chat if you have any questions or want to see some of our content. Tonight, you are listening to Dr. Elena Hyde and myself, Maheen Himani. A couple of announcements for the listeners. We have an upcoming Astro Fair on 29th of August. The tickets are only $30. It is a full astronomy day planned by the observatory and its partners to bring you access to booths, activities, telescopes, an astronomy in action planetarium. Visitors will have the opportunity to walk through the solar system, investigate sundials, and engage with a variety of science-based activities and games all in one ticket. So I highly recommend you to go check this out on our website and grab a ticket while you're there. For those expecting atrium tours, due to construction, they will be on a pause for now. And instead, we will continue to organize pop-up observing throughout next month. And information regarding that can be found up to date on our socials. So go subscribe and follow us on all of our social media platforms so that you can find all of this information.
Oh yeah, absolutely. I for one am very much looking forward to Astro Fair.
Yes, so am I. I missed it last year, so I'm also looking forward to it. It's going to be my first. So I also recommend other people to join as well.
Yeah, and actually, I hope this one will be even better. I will say we'll have extra booths and activities compared to last year. So if you really liked the one last year, good news. Almost everyone's coming back, and we're even getting the 10 Telescopes company, who's going to do a 3D printing telescope demo in the middle of Astrofair. So they weren't there last year, so it's a this year only special event.
Yeah, how can anyone miss that? I think everyone listening should come, even
I,
if you're
well,
listening later.
maybe not everyone. How many people could we fit into the life sciences building? This is a good question.
I'm sure a lot.
Yeah, let's do it. Let's do it. Everyone, come on over. And yes, I totally agree, and I think it's going to be a lot of fun.
All right, so this is a good segue for us to now jump into our space news items. So the
Yes.
first one is going to be covered with Dr. Hyde, and I hand it over to you now.
Yeah, well, speaking of fun, what could be more fun than more X-rays? I can't think of anything off the top of my head, especially if they're safe X-rays that I am reasonably shielded from. So X-rays have been around forever because they are one of the natural forms of radiation that occurs in the universe. But we have some really fun news that's happened recently that is X-ray based. In particular, the Chandra X-ray Observatory, which, if you don't know, this is a space telescope avoiding the the problems with being Earth-based. So Earth's atmosphere absorbs a huge amount of X-rays, the vast majority of X-rays that are out there, which is good because large amounts of X-rays are, as we said, hazardous for human life. But we still want the X-rays coming from space. We want to see the X-rays from interesting stars and black holes and objects. So the Chandra X-ray Observatory has been up for a while. It was launched back in 1999, and it's in the news right now. So Chandra discovered a possible supernova remnant in the galactic center. So Milky Way galaxy I like to tell people who, if you can't see any pictures or artist rendition, I always kind of imagine it as like a fried egg with a little round bump on top. But if you tilt it sideways, it's got the thin disc, and then there's sort of a bump in the middle. Of course, the analogy breaks down pretty fast because we are full of stars. Um, the galactic center would be that one center spot right in the middle, where we have a high density of stars, and we do think that there is a large black hole. Actually, this is one of the other Nobel Prizes that I mentioned before. They have been tracing stars traveling around what appears to be absolutely nothing in the center of the Milky Way, and this is one of the ways where we pin down the mass of the Milky Way's black hole. But in the news right now, as of 2026, June 14th, so yesterday, the article came out. The astronomers found a supernova remnant in an intriguing neighbor in the middle of our galaxy. So this was published in the Astrophysical Journal, and basically, this supernova remnant is an exploded star. These are absolutely vital for providing most of the interesting things on Earth. Carbon, well, carbon can come from all kinds of things, but iron, oxygen, silicon, things that are vital for Earth-like planets and for life as we know it, humans, to form and flourish. So supernovas getting put back into the interstellar medium and helping to form new solar systems are really, really great for life in the universe. And this new supernova remnant, if confirmed, would actually be one of the closest ever discovered to the supermassive black hole region at the center of the Milky Way galaxy. So, as I mentioned before, this is a very dense area. The center of the Milky Way has a lot of stars, and they're close together for stars, but they're not for humans. But they're pretty close together. They're kind of crammed in. You have this galactic center with a supermassive black hole in it, and it's a very disruptive region. So it would be very hard to imagine a cloud of gas and dust, like a supernova cloud, lasting very long in this chaotic central region of the Milky Way galaxy. So you can imagine long, strong magnetic fields, dense clouds of dust around the galactic center. As I say, lots of stuff. But it looks like, and this is, they're still waiting to confirm it, it looks like that they have been able to actually pull in a supernova remnant, which is about 26,000 light years from Earth, and it coming from X-ray data. The Chandra telescope, they also use data from the XMM Newton telescope. But this blob of X-ray emission, what they think probably happened is that there used to be a very massive star that self-destructed as a supernova, which was buried in a larger cloud of expanding gas, and then it sort of had a bit of a little bit of a bubble formed. So it kind of pushed all the gas around it. And this bubble or shock wave pushing against the gas would be bright radio emission. And so they actually have looked at it in radio light as well as X-ray light. Now, this is one unfortunate thing is we no longer have the Sophia telescope, which was the stratospheric observatory for infrared astronomy, which was a telescope on an airplane, which was really cool. We don't have that anymore. It's been retired. But if we did, we could use it to go get more observing for this particular object. So there are alternate explanations. It's still news, hot off the presses. It's a really interesting idea, and they can see what's going on in the region, that they have this sort of shocked or energetic gas, a what's called a hydrogen 2 region, which is an ionized region. There's some sort of material being blown away. What it is exactly, oh, they're not going to say for certain, but they think it could be a supernova remnant. Very fun.
Yeah, this makes me think of how cool would it be if this is true, but then also if there were more stars that went supernova near the black hole, like maybe it could impart a lot of gas and dust within the black hole and feed it, and then it may just become like an active galactic nucleus and like start producing radiations.
Yeah. I know, right? But how much do you need to feed a black hole before it starts, producing jets and getting really, really interesting? Um, mm, and yeah, really fun stuff.
Yeah, yeah, you probably need a lot of material. I wish we could do that like somehow, but we can't, so it's
We just have to
unfortunate.
find a place where it's happening. That's the answer to everything. Somewhere in the universe this is happening. We just need to find it and go observing.
Oh yeah, that's true. I mean, we're not limited to just the Milky Way. We can look outside the Milky Way, so we're fine.
Yeah, it'll be out there somewhere. And actually, listeners, if you know of a system that is currently doing this, why don't you put it in the comments and then we'll list it as a target for potential 1 meter observing.
Yes, and we'll definitely look into it. And this actually goes right in with my next story, which is the fastest wind near a supermassive black hole has ever been found at ultraviolet wavelengths by your researchers. So I'm going to start this story off by talking about the old times when discoveries were made with small telescopes, eyepieces, and long nights outside. But these days, huge telescopes and surveys are producing massive amounts of data that astronomers have to search for in order to find interesting and unexpected objects. One such exciting discovery has been made by researchers at our very own York University. With data from the Sloan Digital Sky Survey, which is known as SDSS for short. And SDSS is basically a project that uses a 2.5-meter telescope in New Mexico to create massive 3D maps of the universe, tracking hundreds of millions of galaxies, quasars, and stars, and has several different surveys. This specific project was led by a York professor, Dr. Patrick Hall, and graduate student Lucas Seaton, with contributions from past and current undergraduate students Mariana Weltri and Zhao Zhu, as well as contributions from researchers at other universities. What they have found is a distant quasar blasting out wind at a record-breaking speed of 30% the speed of light. Quasars, as a reminder, are supermassive black holes at the center of massive galaxies, which are powered by the aggressive feeding of surrounding gas and dust, something like we were just talking about. The intense radiation of quasars can also produce winds from high speed and dust outflow. The quasars that they found, known as J2318, has a mass of 1.7 billion times that of the Sun, which is typical, and is located around 3 billion light years away. The black hole wind detected, however, is the fastest ever seen in the ultraviolet wavelengths. To understand how fast the wind actually is, it can be compared to a Category 79 hurricane, according to one of the researchers, which, if you are unaware of the hurricane scale on Earth, which I wasn't aware of, so I looked this up, it only goes up to Category 5, which is considered catastrophic, of course, so it is like the highest or the worst the hurricane can get. So this is 79, which is like a lot, as an example to kind of imagine chaotic and how big this is. And of course, we have to take into account here that quasar wind is very different than that on Earth. But just as a point of comparison, you can think of it on our hurricane scale here on Earth. What makes the quasar wind different is that they are radiation driven. As I mentioned before, supermassive black holes feed surrounding gas and dust. But when they do this, due to the intense gravitational pull of the black hole, they form a rapidly spinning accretion, and the extreme friction and magnetic forces of which the material causes the material to heat up to very high temperatures, producing energy radiation across the electromagnetic spectrum. This radiation, which is detected in ultraviolet range, is for J2318, is what causes the gas and dust to be pushed outward, producing winds which are faster than ever recorded before in that wavelength range. Something to note is that in astronomy, spectra represent the intensity of light emitted across different wavelengths. So you can think of it as a plot where you're looking at the intensity of light on the y-axis, and then you're looking at the range of wavelengths on the x-axis. And these can be incredibly informative because light or radiation emitted in galactic environments also interacts with particles, leaving their traces in the spectra recorded due to the interaction. So this allowed the team to capture something to note, as was said by one of the researchers, was which that they saw carbon and silicon ions within the quasar intact. So this can be interesting to explore, given that the radiation in this case was energetic enough to drive winds at record-breaking high speeds, yet the associated photons didn't remove electrons from these atoms, which generally there are explanations for these kinds of things, but of course, this is a record-breaking case, and so this could be something interesting to explore how that's what's going on underneath. So in general, such discoveries of black hole winds that come out of observations are highly valuable in understanding galaxy evolution. This is relevant to how supermassive black holes exchange energy with galaxies, which, as seen, can push away gas and dust from within galaxy, expending the raw material needed for star formation and thus quenching the birth of stars in a galaxy. And processes like these are often included in computer simulations, which are based on our theoretical model. But when we get observational data and evidence, it helps us verify and further improve, of course, that theoretical understanding. So things like this and discoveries like this can be very valuable at large.
Yeah, this is so cool. As you say, just a whole extra area of amazing fast speed objects.
Yes, I completely agree. I
And,
believe that,
oh yeah,
sorry,
go
go
ahead.
ahead. Yeah, I was just gonna say, I mean, I am personally really interested in things going on in the early universe, and although this is not as high of a redshift quasar, but still, when we learn about things even going on at lower redshifts, not low, well, it depends on who you tell to classify what a high redshift is, but I mean like very, very high redshift. So discoveries that like this can be very useful when looking at even the early universe and understanding evolution, how it came to be from the start. So yeah, it's very exciting.
Yeah, and as you go farther and farther back into early universe things, you're going unimaginably far away from the Milky Way galaxy, but you're going into a time of high energy, and high energy objects like, of course, quasars. And I think I saw the York University ping. They did an altered headline for this news item, which called it "the fastest and most furious," which which is I thought was pretty fun because it's 30% of the speed of light, which is an absolute ridiculous, impossible speed for any human thing to go. But it is interesting to note that because space is so absolutely tremendous and these things are so unimaginably far away, they have no chance of ever, directly impacting us. And in fact, if even if a burst of one of some burst of this energy somehow got to Proxima Centauri or something, it still would take around over 13 years, I guess, for it to actually get from the nearest star to us. It's just space is so huge, and these things are so energetic. Thank goodness that they emit light so that at least we can get some good information from them.
Yeah, and a more interesting thing is that the Fast and Furious title is actually in the main paper. So I guess people who look at that paper will want to read it because of that.
Well, or they just really like black holes, which it is pretty cool. And quasars as as objects always let you look back farther towards the beginning of the universe because they are so luminous. You're able to see them even though they're really far away. So even our
Definitely.
1 meter telescope, we've had some quasar observing successes.
Yes, a very powerful telescope indeed. Speaking of ultraviolet radiations, and basically we've been talking about so many different radiations across the spectrum. I'm now going to hand it over to you because you have a story of about radio telescopes. So
Yeah, I thought I'd keep on the high energy high energy signals from the universe. But there's, in addition to quasars, there are other kinds of high energy objects out there in the early universe. Um, it's all kinds of fun things, usually black hole powered or uh, all kinds of great stuff. But there's also masars. And masars are magnetic. It's usually in the microwave portion, and they can arise in all kinds of places. So in astronomy, you can actually have them in on Jupiter. You can get them with you know uh, clouds, molecular clouds, atmospheres. It's some kind sort of stimulated line emission. And so like a laser, so like a laser, but not quite, a maser is a stimulated or somehow energized. So some photons have come in and energized something, basically, would be maybe the best way to say it. But if you look in radio light, which is the longest wavelength light, so this is kind of the opposite of the X-rays we were talking about before, um, the light wavelength gets longer and longer and longer until it's taller than leaps tall buildings in a single bound, incredibly long wavelengths. That's where you're talking about radio light. Now, radio has been a wonderful field in astronomy for quite a while, but it's only now really coming into its forte because it requires a lot of calculation and usually large areas of space. So, for example, the Meerkat radio telescope in South Africa, which was recently in the news, their facility operates over a huge region um, of that South African site. The square kilometer array is actually over a square kilometer in on Earth. So these giant radio facilities um, really are possible now due to the increased computing power. If you really like big data and big data problems and data science and astronomy, radio astronomy is the place to be. So in the news now, it's the Meerkat radio telescope in South Africa. They've discovered what they think is the most distant mega maser even ever detected. So this kind of mega maser is basically a naturally occurring space laser. um, really, really fun. They think it's around 8 billion light years away. So this places it deep in the early universe. So this is not the universe as we know it today. This is a much more active universe, a much more dynamic universe, um, and a much more chaotic universe. So galaxies were having a lot more collisions and all kinds of stuff. Now, if we wanted to um, confirm this, we'll probably need a little more observing, but uh, masers are on this giant scale of the early universe. They basically are operating millions of times more powerfully than a typical galactic maser, so a maser for a galaxy. And what they've done is they started calling them mega masers or gigamasers based on how many um, times more luminous it is than a regular maser. So a mega maser is 1 million times more luminous. A gigamaser is 1 billion times more luminous. So they found a signal that usually requires hundreds of hours of observing, but we're fortunate enough to get it gravitationally lensed. And the Meerkat telescope pulled in the data and basically compiled a little picture of what this maser could be. And it's unusual that in a single astrophysical system, you could get a collection of objects, uh, in this case, two galaxies forming a gravitational lens to bring something this distant into focus. But you can always get lucky, so you never know until you go out and look. And it's another, I suppose, another argument for um, systematic searches, and those are the kinds that Meerkat does. So we might even be looking at more mega masers in the future.
I'm definitely looking out for these things called masers because they have an interesting name, and the thing that I can't get over is that they got something in only 5 hours of observing time that would typically take them hundreds of hours. So I guess anything that is time efficient and finding new things is always a great thing.
Gravitational lenses are really awesome. And yeah, for anyone who wants to get into maser physics, just beware. It's got a lot of interesting bits to it. Now we should probably try to do a little bit of your last story while we still have time.
Yes. Okay. Thank you for sharing your story. I'm gonna go ahead and talk about our last space item today. And this has to do with the James Webb Space Telescope. So, since the launch of James Webb Space Telescope in December 2021, a host of unexpected findings about the universe in its early times have come through, as we know, and one of the very surprising discoveries was massive galaxies that have ceased star formation. Um, and this is only within the first few billion years after the Big Bang. Such galaxies are often referred to as quenched or dead, and the reason quenched galaxies in the early universe came as a surprise was our understanding of galaxy evolution, which held that galaxies would be rapidly growing and producing stars at such an early stage within the universe's history. So when we find things that are in tension with our understanding, we of course want to dig further. And so this was done by a group of researchers from the University of Swinburne in Melbourne, Australia. They utilized further data from JWST and ALMA, also known as Atacama Large Millimeter slash Submillimeter Array, which is also a radio telescope located in northern Chile to explore the source of these observations. We were just talking about a radio telescope. They imaged a massive galaxy called Crystal O2 as it appeared just 1 billion years after the Big Bang, which is when it was in the midst of a massive growth spurt. Crystal O2 is not just a single galaxy, but a massive merging group of galaxies in their final stages of collision. And what was found was that the system was forming stars twice as fast as other similarly sized galaxies. The sensitivity of observations allowed the spotting of a huge plume of gas, almost the same length as the galaxy, extending far away from crystal O2. So it was found that the galaxy had a powerful wind that ejected material at a speed twice the speed at which stars were being formed. And taking this into account, it makes complete sense that the galaxy will soon run out of fuel. And that is exactly what they found in their analysis. It was found that if such a rapid blowout continued in crystal O2, um, it would be dead in less than 50 million years. So essentially, in summary, what we can get out of this is that uh, based on their further discoveries, they found that in quenched galaxies that within the early universe, the thing that is going on with the gases and dust being blown out due to the production of stars is just perfectly aligned with how the galaxy is getting rid of the stars during the growth spurt phase. And so this allows for the galaxy to become quenched. And if this is true for multiple different galaxies in the early universe that are merging with one another, we know that we can expect such a thing to be happening. So it makes sense that so many massive galaxies are quenched in the early universe.
Amazing. Very fun story.
Well, I guess since we've run out of time, it
Yeah,
is
as
time.
always, we could stay here forever, but
Yeah,
um,
so unfortunately, we do have to wrap up. I'm sure people are very tired and want to sleep. Well, everyone, it is time to wrap up our podcast for this evening. Thank you for joining us tonight. You have been listening to York Universe, the Astronomy and Astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Dr. Elena Hyde and myself, Mahin Himani. This podcasts and past episodes are available wherever podcasts are distributed. You can always connect with us on Instagram at YourQ Observatory, PixelFed at Allan I. Carswell Observatory, or on Facebook at Allan I. Carswell Ops. Our website is yourq.ca/science/observatory. And there we have a lot of interesting content. And if you feel so inclined, it is a great place to make a donation to our student-operated not-for-profit observatory. Thanks for tuning in this evening. We wish you clear skies and a good evening.
clear skies, everyone.